So we have a whopping 2 hours left together. And the next section of the slideshow usually takes me 5 to go through. So it's usually like half the day. So this is really like a look at, a variety of materials. Mostly I'm focusing on structural materials. I've got a section at the end on mechanical heating and ventilation systems and stuff. And my inclination is to kind of move through this fairly quickly, because to be very honest, even though I know everybody's here to like talk about materials, all of this stuff, all of this is right from the book. And if you want to really explore like all the materials, that's the easiest part to do that way. So, I mean, I'm still going to go through it, but I think what I'll do is like go fairly quickly. And unless there are questions, I'm not going to like elaborate deeply. So if we, stop on 1 or 2 and have some conversations, that'll be great. But what I really want to do, I want to make sure we have the last hour, because what I did was put together a slideshow of about 8 or 10 of our buildings, which kind of like have all of the materials, but you can actually like see them in context, rather than sort of looking at it material by material. So what I want to try to do is do this part in about an hour and make sure that we leave ourselves a good chunk of time for the actual kind of case study type buildings, because the pictures are prettier and there's, just a lot more context in looking at the real buildings. The way the Sustainable Home Design book is sort of laid out is it sort of looks at a particular material. It starts with like foundations and walls and roof and flooring and all that kind of stuff. And it starts with sort of like applications, like what you would use this material for, some of its key properties, its thermal values, its compressive strength, its density, stuff like that. So you kind of know what you're working with. Describes it briefly, and then looks at like the criteria considerations. So for the environmental criteria, like what its impacts would be, the kinds of things you'd want to check, etc. So what I don't want to do is try to just say all those words, as we go through each material. But I think maybe what I'll do is try to like treat, say right now, the whole issue of concrete in a really broad way, which is to say that if carbon emissions are important to you and having a building with low carbon emissions is important to you, then it's pretty much imperative that you don't use a lot of concrete. When Portland cement, which is the glue that glues the aggregate together in concrete, gets made, you take a particular sort of limestone stock and you heat it up really, really hot, 1400-ish Celsius for a couple hours, and you chemically change the rock by heating it up. And a big part of that chemical change is you drive the CO2 embedded in that rock out of the rock and into the atmosphere. So you've burned a whole bunch of fuel to heat up rocks and made a bunch of emissions, and then you've driven a bunch of CO2 out of the building or out of the rock and made emissions.
I don't know if you want to mention that. That's based on that.
That's right. Yeah. Yeah.
If you were to make a comment on it.
No. I'll get to that in a sec. Thanks, though. So, minimizing cement use in a low carbon building is really important. Otherwise, concrete's kind of like a great material, which is why we use so much of it. It's pretty awesome. You take this powder, you add some water, you put it in any shape, form. It's hard in a few hours. It's really hard in a couple of days. You can do anything with it. It's really strong. Like, it's got a lot going for it. But straight up Portland cement concrete is I believe actually kind of like inexcusable to use from a carbon point of view. Like if you've ever bemoaned climate change and you use a ton of concrete in your project, you've certainly contradicted yourself pretty severely there. So we sometimes use concrete. We try not to use it. When we do use it, we try to do it in a way that sort of like makes best use of the material. So things like concreters, concrete perimeter beams, small amounts used judiciously. And you can also displace a bunch of the Portland cement content in concrete with they're called supplemental cementitious materials, SCMs. So that's things like blast furnace slag, fly ash, really super interesting. We had a student in our program this year from Ghana. Palm kernel shell ash is, you can replace 75% of the Portland cement content and replace it with palm kernel ash, which they have like scads of, and get a really high strength concrete. So there are all kinds of materials that can displace some of that Portland cement content. And I don't know what's common out here, but if you phone a cement batching plant and you ask them like what SCMs they have, and you work with your engineer, we can pretty much in Ontario straight up take 50% of the Portland cement out and put slag in place of it, and nobody blinks an eye like that. The engineer doesn't blink an eye, the batching plant doesn't blink an eye. So right off the bat, we can sort of like, half our emissions footprint.
And you request that, right?
Yeah. But yes, you have to request it, because otherwise they're usually putting a little bit of SCM in their mixes because it's usually cheaper than the cement, but they're only doing it from a cost point of view.
They only do 10%. You can do as much as 50.
You can do more,
Yeah.
But when you get more, then your engineer starts to have some questions, and if you have people working with the concrete, they'll have questions. So usually you can still get a good compressive strength for more SCM, but often your set time increases. So if you're pouring a slab and the crew is used to finishing the slab, and they know that in 45 minutes they'll do this step, and in 3 hours they'll do this step, and then suddenly you give them a 70% slag mix, they'll hate you, because it'll be like, it was 4 hours before we could start to float it, and it was 9 hours before we could put the power trowel on it, and there will be that. But depending on what you're using it for, anytime you're pouring it into forms, you can displace an awful lot of the Portland with an SCM, and it'll be just fine.
If you combine it with recycled concrete, like rubble trench foundations and stuff.
Yeah, so I mean, that's good, but the recycled content, you're really just using old concrete as aggregate. You're not using it as the glue to bind itself back together again. So.
And then total alternate, like magnesium oxide.
Magnesium oxide is one. It still has a carbon footprint. It's just lower. Well, we'll get into some of the alternatives as we go. So that's my little bit about concrete. Try to use it minimally or judiciously, and offset the Portland cement when you can. So there are lightweight concrete systems like AAC, autoclaved aerated concrete, like concretes made with lightweight aggregates like expanded glass, those sorts of things. So these systems get interesting because you're now combining some degree of thermal performance with some degree of structural performance. They're not necessarily better or worse than concrete. You have to really look at each one individually in terms of its carbon footprint and things like that. But there are some really interesting opportunities to kind of combine structure and insulation with those materials. We use one in Ontario. We're really close to a plant called Endeavour. They make these expanded glass beads. And so we've been pouring a lot of foundations where the Endeavour is all the aggregate, and our binder, there's no Portland cement at all. It's lime and then a fired kale and clay. That Endeavour is their byproduct from making the glass beads. They put kale and clay in the kilns to stop these things from sticking together. And it's a really good SCM. So yeah, there are things you can do to avoid cement altogether. Yes, yeah, not structurally, because aircrete, the insulation, the A with the K, that's insulation only. It's got like zero structural properties, but it's a good insulator. Yeah. I'm going to actually get to a slide on aircrete, so I'll hold off on that one until we get there. Yeah. Yeah, we also use the Endeavour mix as a sub slab or subgrade insulation. Because same thing, there's nothing that can deteriorate. It's just basically lime and glass. So it can get wet, but nothing deteriorates when it does get wet. So.
How does it compare in cost between concrete and this?
This is about twice the price of concrete, but when you typically pour anything with concrete, you're then adding insulation. So you sort of have to factor that in. So it's yeah,
that's quite expensive.
Yeah, especially if you're shipping it to here. Yeah, yeah.
So if you're using that residentially, what are you finishing inside of it? If you're using that as the insulation.
It's the structure and insulation, so it's both. And so we're either plastering right on that surface, so doing a parge coat, yeah, or we're embedding strapping, and you can drywall over top of it. Yeah. Insulated concrete forms, not. Oh, yeah. It's about 2, depending. They have different sizes of beads and how structural you're making it. Somewhere between 2 and 3 per inch, depending on how we formulate it. So the lower the R value number, the stronger it is. The higher, it's more insulative, but not quite as strong. So we'll work with our engineer to see like what are the actual loads and kind of tune it from there. Yeah, and quite often, because we're making wider wall systems, like that's 16 inches wide. So even if it's only 2 per inch, it's still an R32 wall.
But it's stronger than perlite.
Yes, right? It is stronger than perlite. Yeah. So this is Durasol, or I guess they're now called Nexstem concrete forms, where they use waste wood chips bound together with cement, and then a mineral wool insert. And so you stack up these blocks and pour the columns with concrete. And this is sort of our, hey, you want to do something a little bit greener, but you don't want to do kooky alternative compliance things, and you want something that's, in our part of the world anyway, quite affordable. This is like a good way to go. The factory's in Hamilton, so it's only a few hours from us. And so, on more sort of conventional projects, that's the way.
How does it compare to hempcrete?
How does it compare to hempcrete? It's way stronger because the binder is basically pure Portland cement, which means it has a way higher carbon footprint. So it's not great that way. If you put hemp chips into cement slurry, you would get this. It's it's pretty much the same thing.
But you still have to now provide for a moisture barrier that's better than just spraying tar on it. Right?
Yeah, yeah. Or some people do spray tar on it. Tar is on your list of things you're willing to work with.
Yeah,
right. So the other sort of like subgrade options there are various forms of rammed earth. So there's been a bit of discussion about rammed earth tires. Rammed earth is what it sounds like. It's take earth and compact it. The mixes for rammed earth are much, they're not very clayey. There's usually only about 10-15% clay content. And what you're doing is attempting to very quickly make sedimentary stone. So you have this mix, it's quite dry when you hit it, like it's just barely moist, and you literally like hit it a whole bunch, and it solidifies. A lot of rammed earth homes, the really sexy ones that you'll see in magazines, is actually have as much Portland cement in them as concrete. It's really just cement and earth instead of cement and sand and gravel. But they look really beautiful, but they're not particularly green. We do a lot with earth bags, which is using, well, actually, just flip to the side, which is using polypropylene, basically grain bag material, which you can buy in kilometer-long rolls before they cut it into bags. And we fill that with a rammed earth mix, and then ramming it. I really like earth bag because it's really fast, it's really easy, and you sort of have the backup of the bag. You know, if things, you know, happen to get really wet or flood or something like that, like the bag will contain the mixture, and because you've sort of rammed it into the bag, there's kind of, even when it's wet, there's nowhere for it to go. So I sort of like that a lot more than exposed earth systems. But we've done a lot of earth bag foundations, really like them a lot. And a lot of people in the construction industry will look at what we're doing and go, "Oh, that's really labor intensive," but you don't have to form it. So, you know, you show up and the same day you're ready to start, you're ready to start. If you've got lines painted on the ground, you're ramming earth, where, you know, having done, you know, both forming and an earth bag. In fact, in this one on the same job, we were super fast. We were way faster with the earth bag than forming. So it's pretty, you know, it's pretty great. I gotta say, it's really like low cost and pretty straightforward. And yeah. Although, you know, it's not, you know, our structural engineers, like, you know, this is what every highway in the world is built on. Like, you know, compacted, like a high gravel content compacted earth is like, it's really well known what the strengths of that are. And it's really easy to figure out how many times a person hitting with a 10 square inch, you know, thing, what, you know, compaction that's going to get to. So yeah, we found it pretty easy to do through the codes.
Are you on a rubble trench here or?
On foot in that case, yeah. But sometimes we've done this full depth, like done a full wall.
Yeah.
But more often as sort of like a grade beam kind of.
Yeah. And then you're using barbed wire in between? Yep,
that's right. Yeah. So a strand of barbed wire in between the courses stops the bags from like slipping on each other.
Are there not power tools?
Yeah, you know what? We've tried that. We get a way better result hitting it by hand because it's really easy to over tamp with a machine. It's really hard to get level because, like, if you pause for a second with the machine, like suddenly you're an inch lower than everywhere else, and now you got to try to get everything else down that inch. Whereas, you know, the tamping is really like, it's like 1, 2, 3, 4, 1, 2. You know, like you can really, and you can sort of feel where you have to do more or less. So it's yeah, we do about 40 to 45 feet an hour, you know, this way with a crew of 4. So it's pretty reasonable. Most times we're doing somewhere between like 2 and 4 courses, so it's pretty easy. There's also compressed earth blocks. I don't know if anybody's doing that out here, but we have a couple of people with block presses in Ontario now. So that's basically doing the same as all of this rammed earth, but a pneumatic machine does it and turns it into like a consistently sized block, which you can then sort of, in that case, we're mortaring them, but sometimes when you put them the other way flat, you can just paint a clay slip in between them and that bonds them. And then there's the good old rammed earth tires.
All 4 of these are value?
Very little. Yeah. Almost all of your structural, especially subgrade structural things, don't have any. Concrete doesn't have much R value. Rammed earth doesn't.
But the Durasol does.
What's that?
Durasol does.
The Durasol does, yeah. But they're nowhere near as strong, right? So but it's the more bubbles you're adding, the weaker the mixes get. Yeah. So there's always that trade-off. But I think one of the things that, you know, people are always like, oh, that's not as strong as concrete. It's like, for residential construction, concrete is only like 95 times stronger than it needs to be. Like, we don't need, you know, this massive MPa that your typical concrete gives you. Like, we could do with 1/10 of that is you know, well within the load. So anyway, I just spent a lot of time on that. So other foundation options, we've used helical piers quite a bit where we are. So that's basically like a metal pier with a screw plate at the bottom, gets mechanically wound into the ground. Really great in terms of just absolutely minimizing site disturbance. Like, basically, you can, when the machine's gone and everything's installed, the site looks like it looked like when it arrived, except there's a bunch of sticks coming out of the ground now. So depending on the type of building and site conditions, we'll use those. And these pin piles are also really interesting. This is like a little precast concrete block that has 4 sleeves cast into it, and you drive these steel rods into them. And because they're sort of making a 4-way tent, they don't sink down and they don't pull up. And it's another really sort of like low impact, low cost way to do foundations. And I throw wood piers in here. And normally, like for a long time, I wouldn't have considered this, but we did a house for a fellow who inherited a big stack of decommissioned hydro poles in Ontario. And he was like, I want you guys to build a house, and this is what we're going to do. We're going to put these poles in the ground, and then they're going to stick up, and we're going to hang everything off it. And we were like, I don't know if that's a really good idea. And he totally sold us on it because he was like, well, first of all, we're going to char the posts. So they're going to last longer having been charred and in the ground. We're going to do lots of gravel around them, make the drainage really good. But he also built the building, the floor deck started sort of higher off the ground. And his thing was, these posts cost me $25 each. They're going to last at least 50 years. And when it's time for them to be replaced, my grandson is going to prop up that side of the building, dig that pier out, put another $25 stick of wood in the ground, and it's going to be good for another 50 years. And we'll keep going that way. And it sort of took me like, oh yeah, that's the same thing I give people about earth plasters. It's like, we have this notion that like the only foundation is like, it has to be like monolithic, huge, massive, strong, and it has to be strong enough. But if it's replaceable and affordably replaceable, then that's fairly reasonable too. No, it's not for everywhere, but there's probably ways that it could be done. So yeah, and sort of last and differently than everything else, a lot of people ask about rubble trench foundations, which is basically digging a trench down to frost-free ground and then filling it up with compacted stone. A rubble trench isn't a foundation all on its own. Like you still have to put something on the rubble trench. Like you can't just really set your building on a bunch of rubble. So there's usually like some sort of perimeter beam or something on top of it, which could be concrete or earth bag or whatever material it is you decide you want to use. But it's a way to not have to extend that material all the way to the frost line in order to get anchoring on frost-free ground. So
You self-fill the pores.
what's that?
You self-fill the pores.
No, like the way the idea is it's compacted. We're usually using like larger stone, like a 1 to 3 inch kind of stone. And the pores are the point. Like, so any water that gets in here goes right down to the drain at the bottom. And so that's part of how it stays frost free because there's no standing water to freeze. Yeah.
As long as you're above the water.
As long as you're above the water table. Absolutely. Yeah. Okay. Structural wall systems. First one here is good old wood framing. Pretty hard to beat good old wood framing in a lot of ways. It's one of those systems, people in the alternative building world like to roll their eyes at all things conventional, but boy, the stud wall is hard to beat for speed, efficiency, use of resources, like all that kind of stuff. It works really well. If it's not enough insulation for you, make a second one. A 2x4 wall as your structural wall and a 2x3 wall as your inside wall is pretty much the same amount of wood as one 2x6 wall. So it's not even that resource intensive. It's a little bit more labor, but so yeah, we use a lot of wood framing and then, bigger sticks, timber framing or mechanically fastened post and beam. All of those are sort of reasonable ways to get a structural wall. Straw bale walls fall into 2 different categories. Here I'm calling them structural walls because they're, you can use them as the load-bearing and structural element of the building. You can also just sort of use them as an insulative wrap or infill. But where they're structural, the way that the structure of the wall works is that the plaster skin is the strong element of the wall system. So it's taking all the loads being fed to it from a top plate beam and carrying them down to the foundation. And so what you have is two skins that are extremely strong, compressively bonded together by a straw bale, so that when they're loaded, it takes a lot of load for them to buckle or twist or delaminate. And yeah, it turns out to be a really strong wall. We broke the testing equipment at Queen's University the first time we tested one. That shocked everybody. So we put 25,000 pounds on an 8-foot long wall and bent the steel beam that they were using before it popped the wall. So they're very strong. This is a photo of one of the styles of prefab bale panels we make. So that's so that the wall and the plastering is done horizontally off-site, and they're just sort of like placed in. But whether you do it that way or frame them on or stack them and plaster them on site, they can sort of be a structural wall system.
How thick is that?
3/4 of an inch is sort of the minimum. Like when we did all the testing, we did 3/4 of an inch to kind of have that as the low end baseline.
So is that your true structural component, or are you relying on the bale?
Nope, the bale won't do anything until the plaster fails, basically. So the same that when you buy a conventional SIP panel that's like OSB and foam, the OSB is taking all the loads and it's not bending like it would solo because it's laminated to the insulation. It's the same kind of scenario.
So do you lay it out? Do you lay it out so you know uniform?
No. No, that really, from a structural point of view, the quality of the bale is almost irrelevant. Like from an insulation point of view, if they're more dense or less dense, that changes. But structurally, as long as our plaster sticks to them, that's really, that's what they're doing.
Do you do pre-compression? You put a strap over?
Nope. No, the whole pre-compression thing was because like you typically build up all the bales, put a top plate and a roof on it, and it starts to sink. But if you get the plaster on before you load it, then the plaster is taking all the load anyway, and it's already straight and square, so you don't need to pre-compress.
Does that explain also then why you don't have any studs at each end from top to bottom plate?
There actually is. They don't show up in the photo, but yeah, there's like a stud at either end. Yeah.
Do they carry any load?
No. Well, they would be second in line. If the plaster failed, the stud would start to carry something. If the stud failed, the bale would carry something. If it all fails, then it falls on your head. But one of the great things about the bale wall system, though, is that even though the straw bales aren't structural, like they would hold the building up forever, they'll keep the roof over your head when everything else shakes off.
Yeah,
so
you don't get the
seismic tests have been great because you can shake all the plaster off, but there's still something that can absorb a huge amount of force. Keeping the building up. So
without getting into specifics of plaster, is there concrete in the plaster?
No, there could be. You could make a mix.
Like lime.
So a lime plaster we use a lot of earthen plasters. So either one.
I make paper too.
Yep. Yep. Anything that's in our testing, it can be as weak as 2 MPa and still beat code in terms of like how it works on a whole wall system. So even a really crappy earth plaster can function structurally.
Manufactured walls, do they come in bales or do you chop them?
Right, those are bales. Like literally all we're doing is the same thing a framer does. We're like making the whole thing lying down so that we're not stacking bales up and then trying to plaster up and fighting gravity. It's all happening on the flat.
clean or like it's like
Yeah, so I mean, the plaster likes to, like, straw offers this whole kind of like meshy surface. Yeah.
Do you talk about mycelium at all?
I'm going to show you some in my buildings example slideshow, because we did a building with mycelium foam last year. So yeah, it's pretty cool stuff. What we did was we actually grew the mycelium on the straw in place of plaster. Yeah. So, and it was great because it grew, the roots grew into the bale, made a really nice bond. It was pretty cool.
But then again, you have to keep it dry, right? The bale starts dry, you put plaster on, now the bale gets wet, you set the wall up, the bale dries out again, back and forth.
Yeah.
That safe zone is there, the wall doesn't rot.
Yeah. Won't spend very long here because we looked at earthen systems for foundations. You can do the same thing for walls with the addition of cob, which can be a structural wall, but doesn't offer much R value. So there are people doing that in sort of more temperate climates, but you know, here or in Ontario, you need to do this plus a whole whack insulation, so it doesn't happen that much. So insulations, I've kind of just grouped them by type, of which there are sub-materials. So like loose fill would include cellulose, sheep's wool, fiberglass, mineral wool, like a whole bunch of things that come in that form. And same with batt insulations. There's a number of different materials that can come that way. I guess the thing that I'd like to point out here, batt insulation, especially for new construction, is rarely the right thing to do. It's very hard to, insulation is going to work best when the cavity you're putting it in is completely filled with the insulation. And any time that there's a gap between what the insulation is in and the border conditions, you're going to get a lot of convective loops that really rob the R value. So, when you put in a batt, if it's squeezed a little bit and it has a little wrinkle in it, and then you put drywall in front of it, that channel where that wrinkle is going to allow air to convect in there, and it diminishes the R value really quickly. So in general, like for these types of installations, I would steer people towards the loose fill, where you would like dense pack those materials into walls, and you're much more likely to get a really complete, full, gap-free installation than you are with batts. And like all of the different kinds of materials all have different qualities, right? So cellulose, if you're thinking about carbon, half the weight of the cellulose is wood, it is carbon, so it's storing. If you're using fiberglass or mineral wool, that's a material that you've had to melt either rocks or glass to make. So obviously there's been a pretty big carbon emission associated with doing that. So performance-wise, they're all very similar. But if you're thinking about carbon footprint and also health, like lots of the fiberglass and mineral wool batts, the glue that holds them together has formaldehyde in it. So if you're trying to do a formaldehyde-free building, you'd have to watch for that. Typically borax, so not a major human health concern. I mean, you would want to breathe tons of it into your lungs, but in terms of something in your wall, not really a concern in the same way. Board insulations, again, this covers like a pretty wide range. Wood fiber board, cork board, mineral wool, and fiberglass. They're all things that you can put on the exterior of the building to kind of help break all the thermal bridges when you're doing wood frame construction. And same thing, the plant-based ones, the wood and the cork are going to be carbon sequesters. The mineral wool and fiberglass are going to be carbon emitters. You might notice in all of this, I haven't even included foam in any of these things because I just don't think we should be including it. I'm not even going to talk about it. It doesn't exist.
So how come you don't talk about hemp batts and hemp boards?
Yeah, hemp was in the list of batts.
Okay.
There is no hemp board that I can get my hands on in this part of the world right now. So, but yeah, we actually just did a small job this year, all with hemp fats. It's great. Worked out really well. Yeah. Expanded mineral insulation. So that's things like perlite, vermiculite, expanded clay, and expanded glass. They can be loose pack wall insulations. They can be loose pack ceiling insulations, or you can use binders with them as well. They tend to be a little bit more expensive, but for if you're working with clients who in particular have either concerns about mold or about fire, these are really nice options because they don't burn and they don't really support mold growth. Relatively impervious to water, like they get wet and they dry out and nothing happens. So that would be where we would use those. Here's a thing that some friends and I made up, a category of insulation called bonded cellulose insulation, which is basically hempcrete or straw clay. So cellulose being their plant-based stems, and bonded being something's gluing all those little pieces together. So in the case of hemp, it's usually a lime-based binder, and in the case of light straw clay, it would be clay. We've also done hemp clay, and we've done straw lime. Straw lime is a disaster, don't do that. It gets really dense really quickly and doesn't do much for insulation. Hemp clay worked just fine, but you have a much longer dry time. The hemp lime, when you use a hydraulic lime binder, there's a fairly large degree of chemical set to that. So it does still have a dry time, but nothing like clay, which just literally has to dry. So that's...
Is that a K element? Or
that could be whatever kind of clay you have access to. Yeah. So it could
magnesium as a binder in that hemp?
Yeah, I've played with that on a small scale. And you know, to be honest, the magnesium seems to be very temperamental. And so, you know, I don't have the ability to formulate and batch the magnesium in a way that I know what kind of result I'm going to get, but somebody could. And I think it would be...
We did it with magnesium phosphate, magnesium sulfate.
Yeah. And
it really speeds it up.
Great. Yeah. Yeah. No, I think there's lots of room for that that kind of stuff to develop. Somebody's asking about aircrete. So this would fall under what I call cementitious foam insulation. So this is now getting light enough that it has, you know, no structural capability, but it's got a great R value. The aircrete that we put into projects is about just over 4 per inch. It's kind of expensive, but again, if I have a client that is really, really concerned about mold or those types of issues and or fire, this is a great way to go. And it's a really nice retrofit material because it's easy to pump into existing cavities and it fills them really well. Quick look at some roofing, metal sheets or tiles, cedar shake and shingle. You know, obviously, you know, you would weigh all of these up according to all those criteria, but we've used both for various projects. There's a whole range of mineral tiles from slate to clay tile, cement tile, things like that. There's living roofs, which I'm a really big fan of on very large buildings and not so big a fan of on houses. You know, if you're looking at sort of resource efficiency, carbon footprint, those kinds of things, the amount of extra material you throw at a green roof to make it a green roof, unless there's a benefit, which if you're roofing a 3-acre industrial building, there's a real advantage to having that much greenery replaced. If you're doing a home and it's surrounded by greenery and you've now expended all these resources to add, you know, 600 more square feet of greenery, maybe not. But there are other reasons. You can grow food on them. They're nice to sit on, so they're not something to not consider, but they do tend to be fairly material intensive. My favorite roofing in the world is thatch. I actually went to Denmark to learn how to thatch. It's super easy, super fun. Came home and made the first code-approved thatched roof in Ontario. They wouldn't let us put it on the building, but they let us put it on the entryway. It's now, it's in its 10th year. It's doing great. There's never been a drop of water come through it. When I was in Denmark, we were replacing roofs that were between 50 and 100 years old on the edge of the North Sea. Like that's how long they last. Only roof that I've ever worked on that's fully compostable. Just, they're pretty awesome. And where we are in Ontario, I don't know if the same's happening here, but Phragmites have turned into a really bad invasive problem. Like all kinds of wetlands and marshes are being overgrown with them. So I went to Denmark, I learned how to thatch. I looked at the material they were using. That's one of the pictures on the left there. And I came home and I was like, oh shit, that's what's growing on the side of the highway. Like this is this problem weed that everybody's talking about.
It's
So
illegal. It's an invasive weed.
yeah.
And
Yeah.
therefore we can't grow it in Canada. We can't make it commercial.
No,
The
but
Danes and the Dutch are doing it.
yeah, what I would like to do is just harvest it where it's already growing, which
Yeah.
is basically on the sides of highways, because it's a saltwater reed. It loves being beside.
Mini bamboos.
Yep.
Yeah.
Yeah.
Was it like horsetail?
No, it's like a tall grass.
Yeah, it's a tall grass. Like it's typically like,
Oh, I heard
8, 10 feet tall, as big around as your finger. Okay. So I've left out a whole whack of materials that are in the book. We aren't going to look at, flooring, walls, finishes, all that kind of stuff. But just sort of to give you a sense of like in all of those areas, there's a pretty wide range of what's out there from, things that are conventional and like reasonable in terms of their footprint to things that are conventional and really good in terms of their overall footprint and things that are like less than conventional and also have a lot of benefits. So you can sort of wade through that, or if we have time at the end, you can ask questions. You'll see some of the finishes and floorings and stuff in some of the sample buildings I'll show. So I'm just quickly going to go through some of the mechanical side of things. So, water collection ranging from surface water, where that's available and appropriate, to wells, to rainwater. And then obviously if you're in a municipality that's serving up municipal water, there's that. All of which have, their strong suits. You can learn lots about rainwater from Robin Michel's book. It's been interesting as we have started to do more rainwater collection in Ontario, how much I like it and how well it works. Like, everybody who we've proposed it to, who's been concerned about running out of water, nobody has run out of water. People who've been concerned with, how will the quality be like, the quality's always been really good. And in terms of costs, unless you can drill a very shallow well, you're going to spend a lot less money on a really kick-ass rainwater system than you are on, drilling 50 or more feet. And you have like pretty big energy savings in terms of, only pumping from a couple feet below grade versus, pumping from way down in the ground. So just to say, like, it's really worth your consideration to think about that as a viable option. And then on the flip side, on the waste treatment side, if you're in a municipality, there's whatever system your municipality has, and it's worth looking into what your municipality does. Like, they vary wildly. There are some municipalities that have really awesome sewage treatment systems, and there are some that are atrocious, and there are some that don't have any. So, if you look into your local system and it's reasonable, then maybe it's not worth spending all your time and money and effort and goodwill with the building department and stuff to avoid using it. But if you know that your city's just dumping tons of raw sewage into your waterways, then you might want to step in and do something. So septic systems in the alternative world get a bit of a bad rap, but really they're just whatever you put in kind of comes out right close to your property line. And so, you know, the liquids flow out to the weeping field. What I find very interesting about this system, especially when you start talking to building officials about alternatives, is the whole function of this system is based on an active microbial colony happening out here in the drainage field. Whereas if you propose anything that actually requires active microbial colonies in any other form, everywhere is like, what, you're going to rely on bacteria? It's like, what your accepted solution is, you know, entirely reliant on bacteria. If there's no active bacteria here, nothing is happening, and the system has failed. So, so the big problem with septic systems is not so much what happens here, because it's pretty easy to treat the system well and encourage good microbial activity. It's the fact that it's not really treating the solids, and that at some point you're going to have to take those away and deal with them somehow. And again, if where you're taking them to is a really kick-ass municipal facility, that's great. If they're ending up raw on a local farm field or going to a municipal water system that's just going to flush them into the lake, then maybe not so good. And then there's sort of tertiary systems. So the whole constructed wetland notion is very typically just a step in between the septic tank and the weeping field, where, again, active microbial colonies down here in the filter medium, you know, do a bunch of additional water treatment before that water goes to the ground. But still, solids are something you're going to have to deal with later. And then the other option being composting toilets. We spent a bit of time talking about that earlier, but a few different kinds. There's the very simple sort of bucket batch toilet where you know, you put stuff in, you take the bucket out, and it's composted elsewhere. The kind of all-in-one systems where you sort of have a toilet that's also a receptacle. I would pretty much blanket say don't ever do that. Every compost toilet I've ever seen that people have had problems with, or if somebody's telling me they've experienced a really bad compost toilet system, it's almost always these, because they don't, at least here, it's a pain that the bucket gets filled and you have to deal with it. If the bucket gets filled, then you deal with it. Here, it gets filled because it's not much more capacity than a bucket, but there's nowhere near enough capacity for enough time to elapse that actual composting is going to happen. So instead of taking out a bucket that's actually easy to carry and cover, you end up dealing with a big, wide, flat tray that's it's always going to go wrong. The only time those work well is like in facilities where like you only use it on weekends, and so it has a lot of time to dry out and catch up and not get overloaded. And then there are remote composter systems where you have a composting chamber that's big enough and well designed enough that everything spends enough time in there to, if not fully compost, at least get to the point where it's not unpleasant to deal with. And those can be straight chute systems where it's just like a hole going into that. They can be low flush systems, or we've now worked with 2 different types of vacuum flush toilets that work going to these kind of chambers, which work really well because you're not limited in the toilet placement needing to be right above the tank. The vacuum flush ones can actually go up. They can go 50 feet horizontally and up to 10 feet high than where the toilet is. So it really frees up the design. And it also means the vacuum flush, these ones, if energy efficiency is really high on your list, you can't really do this because this requires constant fan-powered ventilation. It basically requires you to suck all the nice warm air you've spent heating out of your house at a fairly high rate and exhaust it outside. And so when you move to the vacuum flush, like the toilet is actually sealed, so you're not counting on like having to suck air in here and then back out there. You can deal with venting this by bringing in outdoor air and sending it back to the outdoors. So
they kind of suck and blow.
yeah, I do indeed. Yeah.
What's your opinion about the cubeless milk room system with the slope wall? Or with the slope wall?
I lived with one for a couple of years. It works fine. It's not the best it's not the easiest thing to service. So Clevis multrum, the tank is sort of like long and deep, and the back has a slope. And literally what happens is new deposits happen back here. And because of the slope, like as the weight builds up back there, older stuff kind of slides forward, new stuff piles up the back. And by the time it's all pushed itself to the front, it's more or less composted. So it does work relatively well, but you still kind of have to service the pile at the back. Like there's a lot of like reaching.
You can throw your kitchen scrap, you can throw it as a peat moss.
Yep. Yeah.
You can have a bucket with wood shavings next to your phone.
Yep. Yeah, all of that works well. I think there are systems that are better in terms of like how easy it is to extract material, and Phoenix is one that I really like, better than the Clevis multrum, but the Clevis works fine. Yeah. Gray water systems, again, just sort of really quickly, there are the kind that have a storage tank so that solids settle out and liquid goes straight out to landscape. There are some systems that do some degree of that indoors, where you have a small tank and sort of indoor, either in-house or greenhouse type planters, and then the excess goes to landscape. And then I would agree with you, Rob. There are the sort of the rack type filters that attempt to do all of these things indoors and almost always get taken out of people's houses, sadly. So. Energy-wise, we've pretty much only exclusively used PV for a long time. As the price of photovoltaics has plummeted, I can't even start to think about building a small wind tower for what I could put enough PV to run the house on, and then I've got a wind tower that I've got to service this thing that's up there, and it's it can work, but it doesn't work very often. And I have lived with a micro hydro system, which was the best thing in the world, but it's really hard to find the circumstances where you as the homeowner can actually access that water, use it, put it back without, losing 10 years of your life to red tape and all that kind of stuff. So really, like, as far as renewables go, pretty much, you're looking at PV. We talked about passive solar in terms of like its contribution to heating. You can move to more active systems where you're heating up fluid and then sort of storing and transferring the heat in that fluid at other times. Again, probably maybe more practical here where you guys get more winter sunshine. In Ontario, you'd be hard pressed to get more than like 40–45% of your total heat output from solar, just because we can have 3 weeks of low cloud in the winter, so there's not much going on in the way of sun.
What's your personal take on heating hot water?
My take is I love solar hot water because it's so straightforward and resilient, and I can even make the system myself if I want to. But practically speaking, the cost of PV is now so low that it's actually cheaper to put enough PV on your roof to make hot water electrically than it is to put up solar collectors and do the same thing. So
8 years ago, I installed a whole bunch of systems for water stuff. Constantly flashing.
Huh. Right. Yeah, I mean, it's hard to. PV has no moving parts. It's pretty sweet, and yeah, the solar things have. Yeah. 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 I mean, when we do use it, we tend to use wherever possible, like a straight up thermosiphoning system, so that we're not driving pumps. And that again gets into the whole like how much do you want to like be involved. Like if you want to open and close valves, you know, morning and night on sunny days, you can have a system that has just thermosiphons your actual, you know, hot water tank water and doesn't need any pumps and doesn't have any glycol, but you have to help manage it.
Minus 30, literally inside water.
No, well, if the panel's hot, it'll make hot, but then yeah, you've got to know when to shut it down, and yeah. So these two slides are looking at ground source and air source heat pumps. Heat pumps are sort of interesting technology for space heating because they're pretty much, other than solar, your only non-combustion option that's reasonable. And so, I mean, heat pumps are kind of hard to explain, but I'll give you my butchered version. Well, first of all, your refrigerator is a heat pump. So if you think about your fridge at home, your refrigerator is not making cold. Your refrigerator is extracting heat from the fridge box and emptying it on those black coils that are on the back. So you've got heat in your fridge. Doesn't feel hot necessarily, but it's warmer than the set point for the fridge. That heat is being absorbed in a collector plate. The refrigerant that has been heated is then compressed, so it literally boils, and the evaporator on the backside lets that heat go. So if you can sort of see how that system is working in your fridge, extracting heat, even though by heat we mean in the fridge like 4 Celsius, but there's heat to be extracted. There's a refrigerant that's designed to boil at around 4 Celsius when you compress it, and then the heat is extracted when that condenses. So the same thing is happening with a heat pump for heating, whether it's in the ground or outside. If you imagine the coils of your refrigerator being in the house and your refrigerator box either being buried in the ground or just hanging out outside, you're extracting heat, you're warming up a refrigerant on the outside side, and as it goes through its compression and evaporation cycle, it's letting that heat into the building. What's cool about heat pumps is that all that's going into them to make that work is electricity to run the compressor that compresses that gas or that refrigerant. And depending on the unit, you're getting anywhere from 2 units of heat to 5 units of heat for every 1 unit of electricity you put into running that pump. So it means that, whereas, you know, when we talk about gas appliances, we might say, oh, that's 95% efficient. So that for all the available energy in our fuel, we're getting 95% of that, you know, in the building. When you use a heat pump, you're getting 200, 300, 400% of what you're putting in terms of input energy as heat. And you're not combusting anything, so you're not creating any emissions while you do it, depending on what's making the electricity in the first place. So ground source heat pumps basically use either like deep tubing in the ground or a system that's just under the frost line and done horizontally to supply ground temperature to the refrigerant, which then goes to the heat pump, and then the sort of refrigerant that's been cooled comes back in, gets warmed up by the ground, goes back in. So ground source heat pumps tend to be more efficient because they can be tuned. Their input temperature is only going to vary by a degree or 2 because the ground temperature is so stable. But they're very expensive to install. You either have to drill wells or put lots of tubing in the ground, so that the upfront cost tends to be high.
Out here, it's likely due to our super cold nature of our climate and or the shitty construction of the house. I've seen more clients that have failed systems, basically. They stop operating in the coldest months, so December, January, February. They have $2,000 electrical bills. And so then they end up putting another heating system in to compensate for their $40,000 heat system. So the air source heat pumps, I think, are really big out near you, Justin, like where they get to like -20. But most of the time, I think of ground source heat pumps in Alberta as like truck nuts.
Right.
They're like things for guys to show off,
Right.
when they could just put the 30, 40 grand into the insulation on the house, and you know, you would save that money in more efficient insulation.
Yeah, for sure. It's something, you know, anybody who would want to do ground source heat pump, like, I don't think we could ever run a cost analysis where that would turn out to be the best bang for the buck, for sure. On the other hand, air source heat pumps is something we're doing a lot now. In fact, that's almost all we've done for the last few years. The cold climate heat pumps, the ones that work down to the sort of like -25 to -28 range, are pretty awesome. If it was always -28, they might not be so awesome, but you know, where we are, yes, we do get -30, but it's not for weeks at a time. It, you know, tends to plummet a little bit and then come back up. But in the sort of sweet spot of like -10 to -15, they work still really efficiently. So we've gone to those a lot, and they're quite inexpensive to both install and buy the gear for. And so, yeah, we've relied on that a lot lately.
Have you been using the ductless system at all?
Yep, both. We do both ducted or ductless systems, depending on the building and how, you know, how broken up the space is, and whether having only one or two blower heads with the ductless is going to actually move enough heat around to make things comfortable or not. Biomass burning, wood stoves, pellet stoves, masonry stoves, rocket mass heaters, all that kind of stuff. You know, pretty big chunk of things to talk about. We have installed some pretty great pellet boilers in some of our buildings, where the pellet stoves that kind of mimic a wood stove where you see the flame, they're reasonable, but they're not particularly efficient, because the flame that's pretty to look at isn't actually the efficient flame. So we've definitely used those and been really happy with a couple different brands of those. Masonry stoves and rocket mass heaters, they differ from sort of conventional wood stoves in that rather than trying to burn a fire at a temperature that won't melt a metal chimney and won't overheat a building too quickly, you sort of damp this fire down and burn it efficiently. The mass heaters, you feed it all the air you want, you give it really complete hot combustion, and they have sort of, in some way, a convoluted masonry chimney path, so that the flue gases, once the thing is hot, continue to burn until you're burning pretty close to 100% efficient. You're getting, you know, in the 1800, 2000 degree range in here. That masonry core is warming up, and then you have a secondary skin on the outside that will sort of like mean that the really hot core has to radiate out to the other to the outside skin, so that it's not unbearably hot. And so once this whole mass is warm, it sort of radiates its heat out slowly. Both rocket mass heaters and masonry stoves can work really well, but like I was saying earlier, do require like fairly constant firing, because if you let all of this mass go cold, you then need quite a long fire to get it all hot enough that it's working efficiently again. And so, you know, to be really honest, as we've been making more and more energy efficient buildings, combustion style heating is just not working for us anymore, because all of these things just make too damn much heat. You know, like we're making houses that need 12,000 BTUs an hour on the coldest day of the year, and your wood stove is throwing off 50. So it's like, you need 4 minutes of fire, and then you want it to go away, and then it does go away, and then, oh, after a few hours, it does get cold, so you want to light it up again, but boy, then you want to put it right out again. And it's just very hard to sort of modulate when your building is getting into those realms of efficiency. The pellet boiler being the exception to that, because it can sort of kick on and kick off and it doesn't have a long ramp up or sort of cool down time. So those have worked well. But, yeah, I just wouldn't put a masonry stove or a wood stove in an efficient house anymore because you just can't keep it comfortable.
Plus, they're very expensive.
They can be, yeah, absolutely. And the last slide in this section is just looking at ventilation. So earlier on, I talked about how you really can't have an energy efficient house that's not airtight. And I was pretty resistant to the idea of mechanical ventilation because it just seemed like one damn long machine box or something that I needed to keep the house going. But I had a really good friend who was doing building science who sort of got me to reconsider. And the thing that really made me reconsider the notion of having mechanical ventilation is, you know, if you are making an airtight building, you're not going to die of suffocation. Like, it's not like there's no more oxygen in here. We used it all up. We're going down. Like, that's not going to be what happens. But you know, there will be an accumulation of carbon dioxide, VOCs, odors, you know, vapor, shower stuff. Like, all of that stuff doesn't have anywhere to go. And if you intentionally don't make your building airtight, so there's the whole energy efficient thing. So you won't be very energy efficient, but also that means that your makeup air or your exhaust air is being pulled in through unintentional cracks and gaps in your building envelope. So it's like, do I really want the fresh air from my building to be what's like somehow slipping in a weird gap between my sill plate and my foundation, where there could be, you know, all kinds of like gross things that I don't want to be breathing, or like coming in through my insulation and up and in. And so it's bringing particulate from in there, or going through where the mice live and then coming in. So I've got that awesome, you know, mouse urine mix in my air. It's like, actually, no, like from a health point of view, I would like a regulated supply of fresh air from outside, properly filtered. And the thing that my friend said to me was like, if you don't want an HRV or an ERV in your house, first you should get rid of your fridge. Because if you're really concerned about like invasive mechanical equipment, your fridge is way more, you know, energy intensive, expensive, invasive, you know, carbon intensive, all that kind of stuff. We're talking about a fan in a box. So anyway, I calmed down about it, and now I'm a big advocate of mechanical ventilation, partly because I now live in a house that has really like a really good ventilation system, and it's really nice. Like, I don't get sleepy sometimes. Like, half the time when you're fading off, it's because there's too much CO2 in the atmosphere. You're not actually, you know, getting healthy air into you. So anyway, all that to say, there are a couple different options for that. So an HRV stands for heat recovery ventilator. And what's happening in an HRV is that you're sort of like pulling stale air from the house and you're exhausting it through a heat exchanger core to the outside, while at the same time, fresh air is being pulled in from the outside and being given the energy from that, the heat energy from that outgoing air. So basically, you're warming up incoming air with outgoing air. And you can do that. These boxes have varying degrees of efficiency, from really crappy ones from Home Depot that are about 50% to really kick-ass ones from Germany that are like 98% efficient. But you know, they're all doing more or less the same thing, you know, crossing the exhaust air with the incoming air to give it its heat. ERVs, or energy recovery ventilators, are similar, except that what's going on in the box is a transfer of both heat and moisture. So as this stale air is leaving, it's depositing not only its heat, but a bunch of its humidity that incoming air can pick up, which is a really nice feature in a climate like this, or anywhere where it gets really cold and dry, because if you run just an HRV, you keep pulling in dry air from outside and keep exhausting your humid air to the point where you get that scratchy throat, crunchy eye kind of feeling of being in a really dry environment. So an ERV does both a heat and moisture exchange. And so usually they're a box attached to some ductwork, The exhaust ducts are coming from at least your bathroom and your kitchen, and the supply air is going to your bedroom and your living area. You can do more than those, but that would be the minimum. There are also this really cool system called Lunos, which are a through-wall ERV system. It's about the slickest thing I've ever seen. I was super impressed. So it's a tube that goes through your wall. It's not relatively as big as whether it's about a 6-inch tube. And essentially it's a fan with a ceramic core. So this is like a piece of ceramic with a lot of holes in it, and they work in pairs. So they're keyed together. And what happens is this one blows air out through that core. And as the air is going out, the core warms up and absorbs moisture. And then they'll reverse each other once this core reaches room temperature. And this one will start to suck and that one will start to blow. So now this is pulling cold air from outside in through the core where it's being warmed and moistened and coming back in. And then like 60 to 90 seconds later, they'll flip and they kind of keep going back and forth. Really great, especially for retrofits where, you've now tightened up your house, you've made it more energy efficient and airtight. You don't want to blast holes everywhere to run ducts. You can pair up those Lunos in rooms or in zones of the house to get really good fresh air.
Is one system cheaper than the other?
Price and quality kind of are going hand in hand with these things. So the cheaper ones tend to be way less efficient. So the Lunos is operating at about 95% efficiency. The Lunos thing should cost, $120 at Home Depot for what they are. But because they're coming over in small batches from Germany through a distributor in Montreal, and they're like $1,000 a pair. But for what it actually is, it should be super cheap. And hopefully, as they kind of catch on, other brands, domestic brands, will start to show up. Same with the all the really good, not all, but most of the really good ERVs and HRVs are European. There are a couple good North American ones now though too. Okay, that is the end of that section. I still want to show you some sample buildings, but let's take a quickie, another stretch break and
Maybe 5 minutes.
yeah.
My daughter's. They're a lot different. No.
Should take a look at our solar thermal system.
Which one do you have?